In my previous videos, I focused almost exclusively on how do proteins work, what are the sorts of interactions that they form. In this video and in subsequent videos, we're going to zoom out and start asking, how does metabolism work? How do proteins and small molecules interacting in cells give rise to cool biology and biochemistry? So we're going to start with maybe a simple question or maybe a really hard one, depending on your perspective, and that just is, what is metabolism in the first place? So you might recall in a previous video, I talked about how cells use a central favorable redox reaction as this core thing that they build everything around. So in this case, I'm showing a cell that's taking in glucose and is oxidizing it to carbon dioxide using oxygen to do so. This is a favorable reaction that will occur spontaneously, and as long as there's glucose around and as long as there's oxygen around, it will basically run forever. The way cells capture the energy from this favorable reaction is by breaking this single reaction into multiple steps, which I'm showing schematically here with this representation of this molecule of NAD+, which cycles to NADH and then back to NAD+. And this breaking of this single redox reaction into multiple steps lets them do other interesting chemistry. So for example, I'm showing here NADH. If you oxidize it to NAD+, maybe a cell can use that to build fats from acetates. And so what this does is this allows cells to build order, right? They can increase the rate at which they consume glucose from their environment. And in doing so, along the way, by some order where they can say, like this water funnel here, this vortex here, there's ordered stuff happening in this funnel. It's getting this cool, organized, dynamic pattern, but that's actually allowing the water to drain more quickly out of the hole. We see the same thing in cells, right? They build these ordered, complicated interacting systems, but that lets them consume energy faster than otherwise the energy would be consumed. In this video, I'm going to look at, in the context of sort of this perspective, what are the core features that are shared by metabolic systems? And we're going to go through 4 different shared features that we'll see as we dig into different specific metabolic pathways. The first feature is that molecules and energy continuously flow through cells. And what I mean by this is cells must continually take up fuel. If they're using an oxidant like oxygen, they must continue to take that up. They also have to continually dump things out, right? They have to continually dump out carbon dioxide and water. There's no stasis. There's no frozen thing in life. Life always is this process of moving, this process of taking molecules, taking energy, taking them in, and then doing something with them and spitting them out the other side. When a system stops doing this, it ceases to be alive, right? This is one of the core definitions of what a living cell is, or a living system. Second, when they're doing this, cells must be mass and energy balanced. And what I mean by this is for every kilogram, or let's do grams, I'll make it a reasonable size. For every gram of material a cell takes in, a gram of cell material has to leave. Except under the specific condition of a cell doubling its material to say divide, the cell's mass stays basically the same. And even after division, basically what a cell does is it builds up its mass a little bit, then cuts itself in half, and you're left with 2 cells that are roughly the same size. So cells don't net accumulate mass over time, because if they did, they'd get bigger and bigger and bigger, and they would break down, or there'd be other issues. And they have to take in enough to keep replacing what they lose, right? If they're dumping out more than they lose, then they're going to shrink down to nothing, right? So cells must keep the same amount of mass in and the same amount of mass out. Analogously, they have to do the same thing with energy. So they take in energy of some form here, and they dissipate this out as heat. In their glucose reaction, they're taking in glucose and they're oxidizing it with oxygen. The energy that's released in that has to be captured by the cell to do interesting things like move around, but also whatever's left over has to be dissipated out ultimately as heat. They warm up themselves in their environment. And if these aren't balanced, a cell is going to, if wrong way. If we take in, problems. If we take in too much energy and we don't dissipate heat, the cell's going to heat up and die. If we dissipate too much heat out, the cell's going to cool down and die. So there's this idea that everything has to be energy and mass balance. There's this steady flow of material, steady flow of energy. One thing that follows interestingly from this is that molecules in cells are generally at steady state. And so what that means is if I crack open a bacterium, or this group, in this paper here, they actually cracked open bacteria and measured, what are the concentrations of a bunch of metabolites? It's meaningful to say something like, the concentration of glutamate in bacterial cells that are growing, or that are at log phase growth is 96 millimolar glucose, 9.6 millimolar ATP, 0.08 molar NADH, and 0.0004 millimolar oxaloacetate. Those concentrations aren't changing very much because the cell and the concentrations of the material in this cell are at steady state. This is really helpful and really important to keep in mind when we're analyzing metabolic systems, is that the concentrations of the things really doesn't change very much. What do I mean by steady state, or what's another physical example of this? So this is an example from right nearby the University of Oregon. So this is a reservoir known as Dexter Reservoir. It was built artificially through the introduction of dams actually into the reservoir. So there's 2 dams here. And then we have a river that's flowing down from the mountain. So there's basically a net flow of water downhill. But if you say, look inside of the reservoir shown right here, its concentration, its depth, doesn't change very much, even though the flow of water, the actual molecules of water that are inside of the reservoir is changing continuously. So we can illustrate this another way. So now what I'm doing is I'm looking at a slice from up here. We have a high altitude water, and we have low altitude water, and then a dam here. And what I'm going to do is open the pipe to that dam and let the system fill up. And so we've got water that's filling up the different positions on this topographical map, right? So we've got there's some deep water positions here, some other deep water positions here. There's very little water up at this very highest altitude bit. And then this down here matches the water concentration of where it sort of ends up. But what we're seeing is a net flow of water over time. Water is continually flowing down this gradient that's going from the high altitude place to the low altitude place. But if we look at any of the intermediate points, what we see is the concentrations, the depths, the overall fill levels aren't changing, right? The system is at steady state. And so, again, what that means is even though we've got stuff flowing through the cell, the concentrations of the molecules aren't changing. So we can say glutamate's concentration is 96 millimolar. That's the equivalent of saying this tank has a depth of 50 meters of water, for example. And this actually can occur because of this idea we talked about earlier of separation of timescales, right? That since all of the molecular interactions are running really, really fast relative to things like cell biology and metabolism, there's time for the concentrations of things to slosh around and basically come to a local equilibrium, even while stuff is flowing through the system. There's a quick response at the level of the individual reactions relative to the slow response that is all of metabolism. And maybe you don't really believe me. You're like, no, that can't be true. I think that the concentrations of things fluctuate wildly in cells. And they do change in response to things a little bit. But to a first approximation, this really is true. And here's a fantastic example of this. What this is showing is the measured concentrations of stuff in E. coli cells. And this is the measured concentration stuff in some mammalian cells. These are both being grown in culture. Each of these circles is an individual metabolite, say glutamate or glucose or that kind of thing. And what hopefully you'll notice here is that this concentration range spans 7 orders of magnitude on a log scale, both places. And if we draw a line up the middle here, what we see, well, that's a terrible line, but what you can see is the stuff falls on the line, right? And the explanatory power of this is about 0.64. So there's some flow off of the line or some scatter off the line, but overall we're following this trend. And that's really crazy because E. coli and mammalian cells diverged, 3.5, 3.8 billion years ago? Which means that cells have been holding these concentrations roughly steady for billions of years, right? On these 2 lineages going to you and I versus bacteria, sitting there keeping the concentrations of stuff at basically the same concentration. So this steady state thing really is a strong feature of metabolism and of cells. They're keeping the concentrations of stuff relatively close to the same, even over billions of years of time. The last pattern of metabolism I want to mention is that when we're talking about metabolism, we're actually talking about the sum of 2 opposing processes. And those opposing processes can be thought of in terms of the directionality, ranging from more complicated stuff at the top to less complicated stuff at the bottom. So we have catabolism on one side, or catabolism. This is breaking things down, going from more complicated to less complicated. And this is contrasted with anabolism, which is taking less complicated molecules and making them more complicated. So metabolism as a whole is the sum of all of the catabolic processes and all the anabolic processes that are happening. These processes of catabolism and anabolism have their own sort of common features. The first is that they tend to have opposite signs in oxidation. So catabolism tends to be oxidative overall. Like if we look at carbons, they're going to become more oxidated over time. Whereas in an anabolic process, we tend to see carbons becoming more reduced. In general, catabolic processes tend to release energy, whereas anabolic processes require energy, they consume energy. They actually have different redox partners, and we're going to get in a few videos into redox chemistry in detail, but just for now, I'll just point this out. In catabolism, what we tend to see is a molecule of NAD plus picking up electrons and doing redox chemistry and becoming NADH. And in anabolism, what we tend to see is a molecule of NADPH, which is very similar to the other molecule, but slightly different. We tend to see NADPH giving up its electrons, forming NADP+. So there's some similarities, similar molecules, but they have different sorts of molecular features and different signs for the reaction of oxidation versus reduction. And then the last thing is going to the energy side, catabolism generally generates ATP, and anabolism generally consumes ATP. Okay, so we're basically done here. Let me summarize really quickly. When we think about metabolism, what we should be thinking about are cells that are continuously consuming molecules and energy. There's this continuous flow through the cell. But even while this is happening, there's an energy and mass balance happening. So cells aren't net accumulating mass, they're not net accumulating energy. If we look at individual molecules in cells, what we see is that they're basically at steady state. So the concentrations of molecules aren't fluctuating very much. And finally, what we're going to see is that metabolism itself is the sum of a catabolic, so breaking down, and anabolic, building up cellular processes. All right, so that's what I have on that. Hopefully you have a better sort of feel, or you're sort of warmed up thinking about metabolism. We're going to dive into it a bunch of detail coming up, so look forward to that. And until then, see you later.